Welcome back to part 4 on zeros of a polynomial. A real number b is an upper bound for the real zeros of the function if no zeros are greater than b. Similarly, a is a lower bound if no real zeros of the function are less than a. To be able to eliminate the number of possible roots, we can use the following theorem. It's called the upper and lower bounds theorem. Now remember, our whole goal with all these theorems is to be able to throw out some of the possible roots and only keep the ones that are most likely to work. If we let p be a polynomial with real coefficients, suppose p of x is divided by x minus c. Using the synthetic division, if c is greater than 0, and each number in the last row of synthetic division is either positive or 0, c is an upper bound for the real zeros of p. That would mean that anything greater than, because it's an upper bound, anything greater than c can be thrown out. If c is less than 0 and the number in the last row are alternately positive and then negative, 0 counts as positive or negative, so it's kind of like our wild card. C is a lower bound for the real zeros of p. And you might be asking yourself, why do I need to know this? Here's the reason why. Let's say this is your window on your calculator. And of course, your polynomial could exist outside the window. And let's say all you see is inside the box. If all you see was inside the box, you may think, oh, well, I only have 2 real roots. When in reality, you also have a root that is smaller and a root, or 0, that is greater outside the boundaries of your window on your calculator. When it comes to using your calculator, I would say the upper and lower bounds theorem is going to be the most valuable to you to make sure that you've checked for every single possible real 0. So in example 5, we have p of x equals x to the 4th minus 23x to the 2nd plus 5x minus 30. If 5 is an upper or lower bound, or neither, we can check it by using synthetic division. My coefficients are 1, 0 for x to the 3rd, negative 23 for x to the 2nd, 5 for x to the 1st, and negative 30. Dropping the 1 down, I'll use synthetic division and see what happens. 5 times 1 is 5. 0 plus 5 is 5. 5 times 5 is 25. Negative 23 plus 25 is 2. 5 times 2 is 10. 5 plus 10 is 15. 5 times 15 is 75. Negative 30 plus 75 is 45. At this point, we need to look at the signs. 1 is positive, 5 is positive, 2 is positive, 15 is positive, and 45 is positive. If we go back to our rules, it says if c is greater than 0, in this case, c was greater than 0, and each number in the last row is either positive or 0, in this case it is, c is an upper bound of the real zeros of p. Since this is a 4th degree polynomial, it means that there are no zeros or roots x-intercepts above 5. So any values that we possibly found that are bigger than 5, we can throw out. In part B, it asks us what p of 5 is. Well, if we were to substitute 5 into the function, we would get 45 out. Do you remember which theorem this is? By the remainder theorem, we know that the remainder, 45, is also the range value of an input of 5. That was an easy fix. Now let's move on to all the possible rational zeros. In part C, we're asked to list all the possible rational zeros, and then we need to discuss what part A tells us. So again, P over Q is our formal process for identifying all the possible rational zeros. Let's list all the factors of 30. 1. And remember, since they're all going to be over 1, I'm just going to list the whole numbers. 1, 2, 3, 4 is not a factor. 5, 6, 7 is not a factor. 8 is not a factor. 9 is not a factor. 10 is a factor. 15 is a factor. And 30. So these are all my possible integers. Now remember, we have to do plus or minus on all these. Since I clearly found that my upper bound is 5, I can go through and I can erase all the positive numbers that are larger than 5. So there's no plus 6, there's no plus 10, there's no plus 15, and there's no plus 30. That is what part A tells me right here. I can throw out all the positives that are greater than 5. I also know that 5 is not a zero of the polynomial, which means that I need to look at numbers that are smaller. Now mind you, I haven't even graphed this thing yet. So there are a lot of things I could have probably thrown out just by looking at the graph. Let's do that. Let's look at the graph. So I've got x to the 4th minus 23 x to the 2nd plus 5x minus 30. Now notice that my 5, 1, 2, 3, 4, 5, my x only goes from -5 to +5. There's only one interesting root here. I could have rational zeros all the way down to -30. So I'm actually going to change my window as my x min to be -30. My x max is 5 because my upper bound is 5. And let's see where this takes us. So it appears that I only have 2 real roots, which is interesting. I'm going to make my window just a bit lower to accommodate smaller values in the y direction. I'm going to go from -30 to +30, or sorry, +40. Let's graph that and see what it looks like. Okay, so clearly this thing is going quite negative. I have a y-intercept at -30. That means I probably should make my y min be negative 50 and see what happens. Ah, I found a little bounce in my graph. So it looks from my picture here in the graph on the calculator that I have something going on like this. Where this point here is negative 30 in the y direction, and I have some intercept over here on the left of 0, and I have an intercept over here on the right at just under 5. So this is an intercept, an x-intercept that's just to the left of 5. So do you see how this can help you? It tells me that there are no more zeros of this polynomial to the right of 5. There's nothing over here. Now, if I wanted to figure out the lower bound, I could pick a number based on the picture on my graph. It looks like 1, 2, 3, 4. Negative 5 might be the lowest of my low bounds. So if I try negative 6 as a synthetic division, I should be able to show that there are no values that are lower than negative 6, and I could throw out all these other values. Let's try that. So now let's see if my lower bound is negative 6. So if I drop 1 down, I have negative 6. 0 plus negative 6 is negative 6. Negative 6 times negative 6 is positive 36. Negative 23 plus 36 is 13. Negative 6 times 13 is 78, and it's going to be negative 78. 5 plus negative 78 is going to be negative 73, and that's going to be a huge number. 73 times 6 is 438. 438 minus 30 is 408. And now let's look at our signs. Remember, the rule says if c is less than 0 and the numbers in the last row are alternatively positive and then negative, c is a lower bound for the real zeros of p. So let's go back to where we were. I have positive, negative, positive, negative, positive. So this is alternating, which means that I can throw out everything smaller than negative 6. And in fact, I could try these other values, but it appears that the other 0 is very close here. Now, what these values actually are, I don't know. I'd have to use some different methods, but we can definitely throw out some of the values.